Question 4 of tutorial 5. Here we have the given differential equation. Notice that on the right hand side, g of x is a polynomial x times an exponential function. Alright, so we'll solve the complementary equation again, and you see that in this case the characteristic equation has one real root. So we would have this general solution, which, as you will observe, is also a polynomial times the same exponential function. Of course, in this case, the coefficients here are arbitrary, so they are allowed to be any real numbers of our choice. Seeing that g of x is a product of a polynomial and an exponential function, we need to understand what sort of function yp should be in order to produce an expression of this form. This is going to be done by means of taking yp to be given by a polynomial times the same exponential function minus x. If we do have a polynomial times just such an exponential function, and we apply the product rule for differentiation, say a number of times, k times, then what we will get at the end of our process is going to be a sum of terms where each term is a polynomial times the same exponential function. Remember that when we take derivatives using the product rule, we will always multiply the derivative of one term, say u prime, times v, and then we will add to it the derivative v prime times u. But in every case, when you differentiate this exponential function, you produce an exponential function again. And if you have a polynomial, well, then differentiating it again will still give us a polynomial. Therefore, for this question, it makes sense to pick yp to be a certain polynomial p of x times e to the minus x. The question now is, what sort of polynomial p of x should we choose? We can do this by looking at the degree of the polynomial. Once you specify the degree of p, say n, then you can write out a general expression of this form for p of x. We'll have the term of the highest degree and associate to it a coefficient, and you can do so for all the other terms. The solution to this question is essentially going to use a brute force approach. We will be trying polynomials of increasingly higher degrees for a solution. So we will let yp be such that p of x will be a polynomial, and we will try polynomials here with increasingly higher order, so that when we try to substitute this yp into our left hand side, hopefully we produce g of x. Of course, we note that in doing so, it will mean that with higher degrees, you also will have more undetermined coefficients to work with. The larger your degree of your polynomial, the more of these AIs you will have to find out. So we would then need to ask, can we simplify our computations further? And yes, we can. Now, given p of x in this form, let us split it up at the linear term. So by the linear term, I'm referring to this bit here, a1x plus a0. So if I split it up, I will get just such an expression. Here will be all the terms up to the quadratic term, and this would correspond to the linear term. In our case, in fact for all of these equations, the general solution is yc plus yp. What is yc in this case? Yc happens to be, as we have determined, a linear polynomial times precisely the same arbitrary, the same exponential function. Now in this particular form, seeing that C1 and C2 are arbitrary, it follows that this bit here, the linear part of p of x times e to the minus x, can be absorbed into yc. Why can we do this? It's due to the nature of yc. The values c1 and c2 are arbitrary, so they are allowed to take any real numbers of our choice. And if you add a term that is exactly of the same form, then because the constants are arbitrary, it can therefore be made part of the solution of yc. What this therefore tells us is that it is enough for us to have terms in p of x with degree at least 2. That is to say, it is enough for us to start looking at polynomials p where the term with the smallest degree has power 2. And we will make use of this because it will simplify our computations a lot. So let us begin. Of course, in the cases of degree 0 and degree 1, we don't have to consider them because as you see here, yp would be linear polynomial times this exponential function, and as we said, this expression can be absorbed into yc because it is precisely of the same form, a linear polynomial times the same exponential function. So that means we should start from degree 2 and try yp of this nature. A times x squared, because we don't need any linear terms associated to e to the minus x, and of course we have to assume here that a is not equal to 0. So we compute the derivatives. This will be yp prime, and the second order derivative yp double prime. We plug these back into our original differential equation. So we would like to compute the left hand side. Now when we substitute into the original equation, what we find out is that we would have to get a equal to 0. So I'm going to leave this as an exercise because you can just take these terms and plug them in, and what happens is that you'll see that you would need to have a equal to 0. And that is a contradiction because we were forced to assume that a was not going to be 0. So it means that in this case, we can't have any degree 2 polynomial which would give us a solution. So this doesn't work as well. That means we should go further, and it turns out that when we get to the degree 3 case, we are able to get a particular solution. So we will try yp to be of this form. It's a cubic polynomial, and we stop at the quadratic term times the minus x. Alright, so we will differentiate as before, yp prime, and we differentiate further, and we would get yp double prime. And then we go about computing the left hand side when we substitute yp into our differential equation. And now you can see what happens here. By comparing the coefficients, or rather by computing the coefficients on the left hand side, inside of this expression, you will see that the coefficient for this term, x cubed times e to the minus x, will give us 0. Similarly, for x squared times e to the minus x, you would get 0. But for the term x times e to the minus x, you should get 6a on the left hand side. And by comparing coefficients, it means 6a should be equal to 1, because that is the corresponding coefficient on the right hand side for g of x. And finally we see that the coefficient for e to the minus x should be 2b. So having determined all of these coefficients, we compare them on both sides of our differential equation, and we see that 6a equals to 1, meaning that a is 1 over 6, and 2b equals to 0 because there's no such term e to the minus x on the right hand side of our differential equation. Therefore, we see that we have found a particular solution. Yp can be taken to be 1 over 6 times x cubed times e to the minus x when we substitute the values of a and b into our particular choice. Sorry, not that one, but this one here. Alright, so we have determined our particular solution, and therefore we can write out the general solution. It's going to be our CYC, so this bit here, plus our particular solution 1 over 6 times x cubed times e to the minus x. This is the general solution to our given differential equation, and that solves question 4.